Okay, so let's finish chapter 5. So where were we from last time? Excuse me. So we've gone through the gas laws, right? We've gone through ideal gas law. We've done the combined gas law, as they call it, although I call it charbroiled avocados. Okay. We've done Dalton's law of partial pressures, which involves gas mixtures. We started talking about kinetic molecular theory, and we left off kind of starting to talk about the root mean square velocity that you get from the Boltzmann distribution. So we'll do some calculations with root mean square velocity. Then we will go through, I'll talk about effusion, which I'll give you real world application of effusion. So in my research experience, so I'll talk about that. And then we'll, excuse me, we'll end off with real gases. And that's where it gets real. Okay, so real. Because let's face it, we'd all live in an ideal world, but in the real world, gases behave differently, a little bit differently. Okay, so, and what's real right now is I got this frog in my throat. There you go. So last time we left off on talking about the Boltzmann distribution. It's just a statistical pattern that scientists have used to derive the root mean square velocity. In this equation, R is the gas constant, but just to reiterate, it's got different units. So the old gas constant that we're used to using is 0.08206 liters atmospheres per mole Kelvin. If you convert the units on that to be in joules per mole Kelvin, then you would get this number, right, 8.314. And then this energy unit right here is very useful in root mean squared calculations. Kilogram meter squared per second squared is equal to 1 joule. Okay, so this U, I think someone was asking me last time, this U, what does that represent?
Velocity.
Just represents a velocity, so think of it as a V. If you even want to write down in your notes V instead of mu, there's always like kind of a running joke between scientists, say, hey, what's new? And they'll say mu, you know, like what's mu? Anyway. So they call that mu, but it's really velocity. So R is the gas constant in the joules per mole Kelvin units. Temperature, of course, is in Kelvin. And then mm is just molar mass. Okay, so if you see 2 capital M's, always remember that means molar mass. If you see 1 capital M, what would that mean? Do you remember? It means molarity, right? So not to be confused with molarity. Double capital M means moles per liter. Okay, so this was the Boltzmann distribution for nitrogen gas. I'm just kind of retracing a few steps since it's been a week almost since we've seen each other. So the relative number of nitrogen molecules versus the molecular velocity, and then they've got the velocity distributions at different temperatures. So it makes sense that at lower temperature, you would have a slower average velocity or distribution of velocities. So the distribution of velocities is more narrow at lower temperatures. And then of course as you get from, excuse me, as you get from 1000 Kelvin to 2000 Kelvin, the velocities get more broad in nature. So that's something that happens, you know, as you get higher in temperature, you have a broader distribution of velocities. So for nitrogen, at 273, maybe the velocities of those molecules are moving in a more narrow band of range of velocities. But as you increase the temp, you got nitrogen molecules that are traveling even faster still, but you still have some that are still traveling very slow. But the average velocity is clearly further out, you know, for higher temps. This is really kind of a graphical representation of Charles' law in a way, okay? Because as you heat up a gas, the velocities get faster, and that creates an increase in pressure, which creates an increase in volume of the gas. So it's kind of a, you know, way of looking at Charles' law too. Okay, so this is for nitrogen gas. If I had a graph for oxygen, the graph would look a little bit different. And if I had a graph for helium gas, that would look a little bit different. So each gas has its own root mean square velocity. So speaking of oxygen, let's do a calculation for root mean square velocity with oxygen gas at 25 degrees Celsius. Okay, so it gives you a temperature and it gives you a molecule, O2. What's the molar mass of O2? 32 grams per mole. So that'll be our molar mass. The temperature will be 25 plus 273.15 Kelvin, and then we have our R constant. So this would be a pretty easy calculation. So root mean square velocity is equal to the square root of it's going to be 3 times 8.314 joules per mole Kelvin, so that's 3R, and then there's this usable conversion I pointed out earlier. You have 1 kilogram meter squared per second squared over 1 joule. Okay, so that's how we can get from units of joules to an actual velocity when we take the square root of meters squared per second squared. We get a unit of meters per second, which is for velocity, which is what we need. And the temperature, of course, is 298.15 Kelvin. And all of that will be over our molar mass of 32.00 grams over mole. I'm going to convert this grams into kilograms for the molar mass because I got to cancel out these kilogram units here for the energy unit. All right, so it's on a weekend. Do you remember how to convert grams to kilograms? How many grams are in a kilogram? Yeah, 10 to the 3 grams in a kilogram. I know it's silly for me to ask, but you know, it's a typical real mental mistake that happens. So we have 10 to the 3rd grams for 1 kilogram, or 10 to the 0 power, right? All right, so the grams cancel. Mole is in the denominator here, but it's also in the denominator here. So that unit cancels out. We also have Kelvin that cancels out. And we also have kilograms that cancel out. So you can see the units that will come from this will be meters squared per second squared. And then when you take the square root of that, the units will be meters per second, which is velocity. Any questions so far? Yeah.
So why did you put those units, the kilograms, meters, squares?
Well, what are the typical units for velocity, like just in general? Like if I told you you ran from your house to class, what was your velocity? So one unit of velocity that we're used to using is miles per hour. Like that's the velocity of a car, right? But in SI units, it's meters per second. And so in order to get those units of meters per second, we have to incorporate this conversion factor here.
Okay.
So it's just a nifty conversion factor we just throw in there to get the units that we want. It's actually really cool. It's an easy one to remember because it's always 1 to 1. It's 1 kilogram meter squared per second squared equals 1 joule. Really nifty. It's almost probably our second favorite conversion next to 1 cubic centimeter is equal to a milliliter. May sound really weird for me to say I have favorite conversions, but when they're simple, they're 1 to 1, it's like, yeah, it's so easy to remember. Okay, so we plug in these numbers, and what I recommend you do is hopefully have your calculator with you. Try to punch these numbers in and tell me what you get. Because every calculator works a little bit differently, and maybe you haven't done square root on your calculator in a while. Maybe ever, I don't know. So what you do is, some calculators you want to plug this in first and then take the square root of that. Or other calculators work where you have to input square root and then parentheses, and then you got to put all this in there, you know, and then put the parentheses around that to enter it. So try putting it in your calculator, tell me what you get. 482.1? Anybody else get that? All right, good job, you're right. So, it should be 482.1, and the units would be what? Meters per second. So the thing is when you take the number here, just to reiterate the math, you know, if you take the square root of that, you end up getting, you know, just meters over seconds, right? Just to reiterate the math part of this with the units. All right, so the units will be meters per second. 4 sig figs, the reason being 298, I'm sorry, it was 25.0, right? So 25.0 plus 273, this would be your last sig fig right here for the 1, but also the 32.00, but really it's the temperature that tells you, right? 4 sig figs. Is everybody else getting 482.1, or are you able to swing that? Oh, everybody's good with it? Brittany, you're good? Is it working?
I'll figure it out.
All right, let me know if, we'll try another one right now. Okay, so, let's go to the next one. So, so just so you know, so this 3 and the molar mass, even though it's measured, you know, I would say, again, you know, using molar mass for sig figs is really subjective. So I would just look at the temperature to tell you how many sig figs. All right, and this 3, and also the R gas constant, that's also measured, but again, it's, you know, again, very subjective as to how many units you use. The 3 is definitely an exact number. All right, so I always end up just using the temperature because that tells me all I need to know. Okay, so let's do another one. Try this one. Calculate the root mean square velocity of methane gas at 25 degrees Celsius. Did you remember that was called methane? Like simple hydrocarbons? Okay. So try that one on your own, see what you get. Okay, so anybody got an answer yet? So what's the molar mass of methane? Yeah, so if you take a 12.01 plus 4 times 1.01, just using 2 decimal places for my molar mass, you would get 16.05 grams per mole. And of course you have a 1,000 grams per kilogram. All right, so anybody get an answer? 680.8. I got 680.7, but maybe I'm off by one. All right, so 680 point, I'll just put 7. I have to double check this, but. So here's the thing. You just calculate a number from this, right? But what does it mean? Like, I mean, what kind of sense can we make from this? Ben, I see that question?
I did have a question. If we did this problem and then we got like 680.8 or 680.9, would you mark it as completely wrong?
Oh, no, it's just sig figs, right?
Okay.
So for this class, more so than 1 to 7, I would say the sig figs only count as a small sliver of the points for a problem, right? You know, if you get the right answer, you're just off by a decimal or something, it's minor, you know. So I wouldn't sweat that. I'm not that professor, at least not yet. No. So like 5 or 10 years from now, you can tell any younger siblings who might come here, or younger friends who might come here and say, "Oh, we had him when he was still easy." Of course, you're probably not feeling that right now. You're like, "No, this guy's not easy." But yeah, no, I wouldn't mark it totally wrong if you were off by a little bit of the sig figs. Let's talk about the numbers. So comparing methane to oxygen, I think that this is what I want you to see. Does it make sense that methane gas has a higher velocity? Does that make sense? And it should, because methane gas is a lighter gas. So lighter molecules move at faster velocities. Okay, so that's a really important concept I want you to take away from these calculations. It's not just doing the calculation, it's making sense of the number, right? So drawing the physical conclusion, methane gas has a higher velocity than oxygen, right? Because it's a lighter gas. Okay. So another concept from kinetic molecular theory is something called diffusion versus effusion. So diffusion is just when molecules spread out from high concentration to low. In other words, we have diffusion of gases. Just naturally it happens, you know, the gas will uniformly fill a container that it's in. Right? We know that about gases, right? You have diffusion. Effusion is a little bit different. If you have a small orifice, and on the other side of the orifice is a vacuum, whereas on the one side you get all this gas, the gas is going to want to effuse through the orifice into the vacuum. Right? That makes sense.
What's an orifice?
A small hole. Okay. They also sometimes they call it an aperture. Right. So so here in my research as a grad student, we were designing the time of flight mass spectrometer, which I'll show you some data from that. I'm not expecting to understand everything, but it's a really cool application of kinetic molecular theory. So just to put it in context, but we were trying to pulse gases through a really small pinhole, and inside the mass spectrometer is a vacuum. You know, so you got this glass chamber at atmospheric pressure, and you pull out this little stem that plugs up that hole, and when you pull the stem out, this gas gets sucked into the vacuum, and that's the process of effusion. Okay. So effusion is related to the root mean square velocity. This is the equation for effusion. Okay, the rate of gas A divided by the rate of gas B, and this is the rate of effusion now, is equal to the square root of the molar mass of gas B over the molar mass of gas A. So I highlighted this equation, I just want to point out. Notice how it's, for the rate side, it's gas A over gas B, but for the molar mass side, it's gas B over gas A. So it's flipped. Okay. All right, and I could go through a whole derivation of that, but just to save time, I just assume not. So this is a pretty easy equation to use. Here's a diagram showing the idea of effusion. So here's a vacuum. Oh yeah.
What was that equation for again?
It's just sometimes they call this Graham's law. It's just the rate of effusion or effusion equation. But I think in your textbook, maybe they call it Graham's law after the scientist Graham. Okay. But basically, the rate is going to be in meters per second. Right? That's like a velocity rate. Okay. Since it's meters per second in both the numerator and denominator, this is a unitless ratio. Okay. And so you're just looking at it's a relative rate of gas flow into a vacuum. You know, with this Graham's law. Okay, so here's a vacuum, here's some gas chamber. Imagine if you were in a spaceship, okay, and the hull of the spaceship gets punctured. What happens? This is like real sci-fi stuff, right? You know, have any of you ever seen the Alien trilogy or quadrilogy, whatever they call it? You know, the movie Alien, and then there's Aliens, and there's Alien Resurrection, or I don't know, it got out of hand, but to say the least, the first movie and the second movie are worth a watch. Don't watch anything after that. Then the second one, though, you know, you got the lead character, her name is Ripley, she's played by Sigourney Weaver, and she just plays like this badass chick, you know, and she like kills all these aliens, it's awesome. And there's a scene at the end of the movie when she's trying to kill the queen alien, you know, and she's got to get this alien out off the ship. It's like, you got to go, right? And she punches the hull open, you know, like pulls the lever, and the hull opens, and this big vacuum scene happens. And every time I think of Effusion, I think of this movie scene where everything's getting sucked into the outer space vacuum, right? You know. And so that's what's going on with Effusion. If you want to like see Effusion in a movie on a graduate scale, see that movie. You know, it's worth a watch if you haven't seen it. It's like 30-something years old now, but it's worth a watch. Okay. So imagine like an alien and the cargo getting all sucked out into outer space, analogous to gas molecules getting sucked into the vacuum, you know, into outer space. Okay. Sorry, it's kind of a sci-fi moment there. Let's do a sample calculation with this. All right. So it says, calculate the molar mass of a gas that effuses at a rate that is 0.462 times that of nitrogen. So notice I'm adding a few more words in here. Let me repeat what I just said. Calculate the molar mass of a gas that effuses at a rate that is 0.462 times that of nitrogen. Okay, so I just took this as a sample problem from somewhere, but I'm adding a few more words to it. So what does 0.462 times nitrogen mean? Okay, and what it means is it's 0.462 relative to nitrogen. So let's just take, if you go back to the equation for effusion, let me just erase this. Okay, so we have rate of gas A over rate of gas B, right? So what it means is that if we take gas A as being, or excuse me, the rate of some unknown gas A, all right, and that's equal to 0.462 times the rate of gas B, and we'll take gas B as being nitrogen. Now you should be able to take rate of B equals 0.462 gas A if you want it, but the thing is that what they're saying is they're saying that rate A over rate B is equal to 0.462. So let's just translate that a little bit more into English and percentages. Another way of saying this is that you have some gas that has a rate of effusion that is only 46.2% of the rate of nitrogen. All right, so it's going to be a much slower rate than that of nitrogen. Does that make sense? Maybe not. We'll see what happens with the calculation. But this is the setup. Okay, so we know that this is 0.462. Okay, and we know that from that, we know that we have the molar mass of our gases. Okay, so taking nitrogen as our gas B now. Okay. All right, the molar mass of nitrogen is what? 14.01 basically. 14.01 times 2, right? So it's 28.02 grams per mole for the molar mass of nitrogen. And now we have to find out what is the molar mass of gas A.
That's equal to. So that one, what rate A equal, is that what you would put? for-
Yeah. So just going back to Graham's law, okay, you've got A over B, but you've got B over A here, right? Going back to the equation. Okay. And again, the way they worded it, they said, well, we have some unknown gas A that has a velocity that is 0.462 that of rate B. Okay, that's what it's telling us. So how do we solve this for the molar mass of gas A? So let's do some math. Dare I say? Okay. Okay. So what would be the first step to solve this?
Multiply by the molar mass of gas A.
Well, before we multiply by the molar mass on both sides, we got to square. We essentially square both sides to undo the square root. So we're going to go ahead and square both sides. And then what that gets us is 28.02 gram per mole divided by molar mass of gas A, and that's equal to 0.462 squared. And now it gets pretty easy, right? Now the algebra looks real easy.
So I have a question for, okay, so how would you assume that rate B is the nitrogen and then?
Right. So that's the hardest thing with this particular example. It just says the problem asks, okay, calculate the molar mass of a gas that effuses at a rate that is 0.462 times nitrogen. Okay, so in other words, 0.462 times nitrogen. Right, that's like the translation. Times, they're saying literally it means times. Like times, 0.462 times that of nitrogen. Okay, if we picked gas A to be nitrogen, then we would have to take 1 over this to get the right ratio. Right, so just by convenience, we're taking gas B to be nitrogen. All right, if we had nitrogen here and then the unknown gas B, okay, then we know that this would have to be 1 over this. It'd have to be 1 over 0.462. So that's how we know. That's just, yeah. The wording is really kind of tricky. Yeah. That's how we know. Just by the fact that it says effuses at a rate 0.462 times nitrogen. And the word times literally means times. I added the words in there, that of nitrogen, but again, the word of means multiply. Okay, going back to your math 40, maybe even math 20, I don't know, but they usually teach that in algebra. Once you're here, it's pretty easy, right? Now it's just molar mass